Going through our PSS section, right, or the prerequisite science skills, and they've got some kind of simplifications that's just nice to kind of address. So if we had some mathematic simplifications, if we had to write out 4 times 4 times 4 times 4 times 4 times 4, okay, in your calculator, or even into your notes, that gets a bit tedious. So how could we simplify it?
Exponents?
We could take advantage of our exponents, and we could just write 4 to the 6. Okay? You should be aware of this already. If you aren't, now you are. Okay? This makes it a little bit easier. We have to be a little bit careful in entering it into the calculator, because every calculator does it slightly differently. Sometimes you'll see this EXP, sometimes you'll see an X caret Y, sometimes you'll see a Y caret X. Make sure you know how to enter it into your calculator before the exam. Okay? So, the whole point of the exponents is just to simplify your calculations. Terms that you can see pop up, squared and cubed. In those cases, what are we saying?
4 times 4 is squared.
Squared is something to the second power. Because to determine the volume of a square, what do I do?
X times width.
Length times width, or width times height, whatever you want to do. It's those two values multiplied by each other. So I'd get x squared. Cubed?
X to the third.
X to the third. Because if I looked at the volume of a cube, length times width times height, I have those three things being multiplied. Okay. One is volume and one is area because of the dimensions you're looking at. Yeah.
Okay.
Questions about that? Okay. Powers of 10 is going to become very, very important, so we need to be aware of them. Okay. All we're trying to do is shrink or grow numbers without having to use a whole bunch of placeholder zeros. Okay. So we'll use our powers of 10 to show those exponential values. So if I have 10 to the 6th, it's the same as saying 10 times 10 times 10 times 10 times 10 times 10. Yeah. Okay. Or if we did 10 to the negative 6, it's divided by 10, divided by 10, divided, so on and so forth. Okay? So we're using those powers of 10 to help us run simple calculations. Really what that's coming out to is our scientific notation. So if we went through and looked at the distance between the Earth and the Moon, we're looking at 406,300,000 meters. Okay? That's a lot of zeros that I have to trail in there when I write it out. Okay? If I looked at the distance between a carbon atom and an oxygen atom, okay, I don't even know how to say that, so let's just say 0 point bunch of zeros 116. Okay? That's a really small number. I want to be able to simplify and get rid of some of those zeros so that I don't have to write all the placeholder zeros. I only want to write the zeros that are significant. So that's where scientific notation comes in. The format for scientific notation is shown at the bottom. Okay? You will take your first significant digit, and that is placed in the ones place. Decimal point, the rest of your sig figs, followed by your power of 10. Okay, so let's take a look. For that first one, we have 4 decimal point 0, 6, 3. The rest of those zeros as written are insignificant, times our power of 10. Okay? Our power of 10, the n, is how many places we moved the decimal. Okay, well, we started here. We went 1, 2, 3, 4, 5, 6, 7, 8. If you have a calculator that's been used by the math department, you might look at your screen and you might see these stupid little curly cues written underneath each of those sections on the calculator. That's because someone is trying to do this. Okay, they're counting their places. And they happen to do it with a pencil that marked the screen. So we moved it 8 locations, so the n value is 8. Okay. Is the number I'm trying to represent big or small? Big. Big. Because it is big, that is going to be a positive 8. Okay.
You have to indicate that with the positive sign.
I don't have to show the positive sign. Okay. We're looking at just a mathematical symbol here. The positive is always implied as far as a mathematical symbol goes. Okay. To be officially correct, we'd have to tag our meters at the end and we'd have our answer. What about the next one?
It's the same thing, so it would be
1.16 times 10. 1, 2, 3, 4, 5, 6, 7.
Negative 7,
Why is it negative 7?
because it's going down. It's as if it's being divided by 1.
So there's a variety of ways to remember the signs. The way that seems to have stuck with me most recently is looking at the original number. Is that a small number or a big number? Small number. It needs to be minus. That's it. Not shifting your decimal. I went to the right, so it's positive, left, negative, because that, depending on what you're looking at, will change which direction you're going. Look at your original number. Was it supposed to be a small number or a big number? If it's a small number, your power of 10 is negative. If it's a big number, your power of 10 is positive. It keeps it relatively clean and straightforward. Questions about that? Okay. So let's look at one more quick example on this. Instead of that 116 number, I want to write it as 11.6 times 10 to the, yes, I should be able to count this without doing this, 2, 3, 4, 5, 6, 7, 8. Are those numbers equivalent?
No.
Yeah, they're absolutely equivalent. Are they both scientific notation?
No.
No. Only the blue number is scientific notation, because in scientific notation, my first significant digit is only allowed to show up in the ones place. Okay? The black number, I have a 1 in the tens place. That's not scientific notation now. Okay? I think this is incredibly stupid, okay? But that is the definition of scientific notation. Okay? Definition says you can only have your first significant digit in the ones place, nowhere else. This is now proper scientific notation. The black number is a power of 10, and yes, it expresses the same meaning, but it is not scientific notation.
Is there a reason for it or just arbitrary?
It's arbitrary. Yeah. Kind of goes back to our rules for nomenclature. I could have written out the formula for sodium chloride, right? Or not our formula. All right, if I did sodium chloride, well, actually I wanted this, NaCl. Okay, so my name would be sodium chloride. What's the charge on the sodium? A +1. So why don't I write sodium 1 chloride? Isn't that valid?
Yeah.
Yeah, that's true information, but
It's too much.
it's wrong as a name because I'm adding more information than what is required. Okay? Same thing back to the scientific notation. It's a definition. Okay? That admittedly I've gotten wrong. That's why I call your attention to it. Okay? Make sense? Okay. So let's take a look at some measurements. Okay? How many sig figs in each of those measurements? How about the first one? How many sig figs? 1, 2, 3, 4. Second one. 2, 3, 4, 5, 6, 7, 8, 9. Last one. 3. 1, 2, 3. Okay. So what we're trying to do, or what this slide is attempting to do, and then screwed up pretty thoroughly, okay, is looking at our sig figs and trying to convert these across into scientific notation. And if we went through and did it, 4.063 times 10 to the, this is our 8, right? Okay, 8. I could go through and do it for the next one, and that would really suck, so I'm not going to do that one. Okay, 406 million. Well, million is 10 to the 6. Okay, that's not scientific notation, so it would be 4.06 times 10 to the 8. I add 2 more because I had a bigger number, right? Okay, the middle one I don't even want to write out because there's too many numbers in there. What if now we look at just that first number, Okay, yeah, ignore that. Sort of a inside joke. Let's take a look at that first number. So in that, there were only 4 sig figs, right? The person that actually did that measurement did not measure by hundred thousandths, measured by thousands. How many sig figs in that measurement? Okay, so now what we're doing is not evaluating the number, but how the measurement was taken. If we look at how the number's written, we only have 4 sig figs, and that goes out to the 100,000 place. Okay, so we're saying the last significant digit is the 100,000 place. The person that took the measurement measured with accuracy to the thousands place.
So we have 6.
Why do we have 6?
Because the measuring device goes out to 6.
The measuring device measures to thousands, which means those 2 zeros are significant. Is the number written where those are significant? No. How do I write the number so that those become significant? Okay. So I heard a suggestion for a decimal point. What happens if I draw a decimal point? Okay. Not there. Okay, so let's draw the decimal point over here. That changes the value. Now it's not 406 million, it's 406,000. It can't change the value.
4.06300 times 10 to the third.
4.06300 times 10 to the third.
That just looks ridiculous.
Third, let's convert. We need to slide the decimal place 3 locations, making it a bigger number. So I'll go this direction. That's 2, there's 3, and I end up with my answer of 4,063. Is that the same as 406 million?
What if you change it to the 8 then?
What if I change that power of 10 to be 8? Now what happens?
Now it equals the other number.
Okay.
Okay.
There it is.
Now I'd get the correct answer. And by writing it in scientific notation, what am I drawing attention to? The correct sig figs. So there are cases where we will use scientific notation to draw attention to zeros that are not placeholders, but actually hold meaning of not 1 through 9. That's where scientific notation comes in handy. Okay. Kind of a weird, loopy one to look at, but that's what's happening.
So it gets more complicated with more advanced equipment we use.
It's not necessarily more advanced equipment, it's what the equipment reads out. Because 0 has 2 meanings. It has the meaning of not 1 through 9, and it has the meaning of don't put a number there. Okay? We have a placeholder and we have meaning. The significant digit is meaning, the placeholder is not. So depending on how our measurement comes out, we may end up taking a measurement that looks significant or isn't significant. We have to clarify the meaning of that 0. That's where scientific notation can help us out. Does that kind of make sense? Okay, it's this weird kind of nebulous stars have to align to get perfect zeros. Okay? If your instrument gives you perfect zeros, those don't disappear. Okay? This is your balance, right? You got there's your little disc, right? Little shield around it. Okay? And I put some stuff on that disc. And what it reads out was 0.5. Actually, let's do it this. It reads 5.000. How many sig figs? 4. If you wrote that in your notebook as 5, you're now wrong because you've removed the significant digits. Okay? You would have to include those zeros in it. Okay? If it read out 50, okay? That 0 right after the 5 is significant. Okay? By including the decimal point, I can ensure that those digits are counted appropriately. Okay? Without the decimal, like our original number, our 406 million, we don't know what the zeros mean. The instant I can bring in a decimal, I can now say this 0 is significant, these other zeros aren't. Okay? That's where the scientific notation can come in and help you out. Kind of makes sense? Okay. So now we move into chapter 2, looking at our metric system. Okay. Your textbook refers to these as the basic unit for our metric system. I will refer to it fairly consistently as the core unit. Okay, and we'll look at why I call it the core unit in a little bit. Okay, so whenever we take a measurement in length, our core unit will always be meters. Mass, our core unit is grams. Volume, our core unit is liters. Time is seconds. We can manipulate and change those units to scaffold into different scales, but for the most part, those are the core units that we'll deal with. So far, so good? Okay. Why do we pick the metric system and not use the American system? It's not necessarily more accurate, believe it or not.
It's easier to measure because it's all 10.
What's the history behind our American system?
More people use it. We didn't like the British, so we made our own.
Well, actually, Greece.
It's based off of the Greek. I actually blamed it on the British. But it's actually Greek, right, for feet and inches. Right? The inch was the distance of the king's knuckle. A foot was literally the length of the king's foot. What happens when the king dies?
A foot change.
You get a new foot, you get a new inch. Okay? Everything changes. Okay? So we don't want a measurement system based off of a person's life, because when they die, our system now falls apart, and we have to reinvent the system and reinvent our conversions. Okay? Why did we stick with inch? I don't know, but we did. Okay? And we're now well past the point of no return. It's never changing. Okay? That's just where we are. So science has stuck with the metric system largely because of the powers of 10. When we look at inches and feet, well, there's 12 inches in 1 foot. We're looking at powers of 12. Right? 12 times 1 is 12 times 2.
24,
3,
36,
4,
48,
5,
16,
7.
72.
I said 7, didn't I? 12 times 7 was 84. 10.
120.
120. Notice that as we're doing this, there's probably a few of you that are just being like, I'm not going to say that. That's too easy. Okay? But let's switch it to our metric system. 10 times 9.
90.
10 times 100. 1,000. We can do powers of 10 in our head very quickly. Powers of 12, not so much. The powers of 10 allows us to scaffold and scale things much quicker than our measurements within our American system, so we tend to stick with the metric system. That power of 10 not only works with length, but we also use it for mass, for volume, and time. So we can use the exact same scaling factor for all our measurements. That makes life a little bit easier when we go through to do conversions. Okay? So, this means we have to interpret our powers of 10. When we scale up or down, we will affect the core unit. We'll affect the core unit by introducing these new symbols. Okay? Tera, giga, mega, kilo, deci, centi, milli, micro, nano, pico. There's also femto. Okay? There's all sorts of other prefixes that we could drop into these. You've already heard of some of these. Okay? When you measure volume, typically what volume are you measuring? In lab. Milliliters. You're looking at the prefix of milli affecting the core unit of liters. How is it affecting the core unit? Well, instead of it being just a liter, the milli says I'm taking 10 to the minus 3 of said liter. If I can remember the powers of 10 and tie them back to the symbols, whoops, okay, I have an easy way to convert between differing measuring systems. That's the point, or the power of our scientific notation, or our metric system. Right? You are responsible for knowing those. Right? There's really only 3 that you will encounter: kilo, centi, and milli. So what you need to do is memorize those 3. Kilo is K, which means 10 to the third. Centi is C, which means 10 to the minus 2. Milli, M, 10 to the minus 3. You can go through and memorize your 100,000, whatever you want to do for the multiplication out. I do not recommend that, but that is up to you. What I recommend you do is memorize your powers of 10 and tie the powers of 10 back to the symbol. Okay? It can simplify your calculations, particularly if we set up our dimensional analysis remembering these powers of 10. Okay? Let's take a look at how they're used. Actually, sorry. You're officially responsible for all of them. Those 3 are the ones that you should memorize. I said that, didn't I? It's been a long morning. Okay? You need to memorize those 3. Okay? Absolutely. Does that mean in the homework you might be asked questions about the other ones?
Yes,
Yes.
of course.
Look it up. I don't expect you to have them memorized. Just look it up. Okay? Why do we not look at tera, giga, or mega? They're too big. We aren't going to measure a teraliter. Okay? That's a little bit outside of the scale or the realm of things that we can work with. How about a picosecond?
Not really.
Okay. That's a really, really, really tiny time frame that becomes very difficult to measure. It actually requires special equipment to measure at that scale. Okay? So we won't look at those units. We tend to sit just at the kilo, centi, and milli. Okay? Some of the others become relevant, but much less so. Okay? So, how would we go through and use this? Well, if the number is 1,200 meters, what I'm trying to do is convert this now into scientific notation. So this will be 1.2, as it's scientific notation, times 10 to the, how far did I shift my decimal? 1, 2, 3 places. Okay. Is my original number large or small? Large, which means that is 10 to the positive 3. The unit was meters. What is the number and the new unit? Well, the number will be 1.2. What's the new unit? What does 10 to the third mean?
It's kilo.
Kilo. 1.2 kilometers.
That's easy.
That's why we do this. Okay? Do the next 3. If you've got questions, raise your hand. I'll come to you. Okay. How far did I shift the decimal? 1, 2 places. Was my original number small or large? Small, so that needs to be negative 2. What does power of negative 10 to the negative 2 mean? Centi.
So it's a centisecond.
So it becomes 1.2 centiseconds. Make sense? Everybody got them? Okay, so I can move on. Okay. The next part is dealing with fractions. When we move into chapter 2, we're really talking about conversions, and everything we do in conversions is looking at a fraction. Okay? Most people tend to freak out at fractions, but that's what we're doing, and if we can get used to just using fractions, we're okay. Other things that we can do with fractions is proportionalities. Okay? Everybody goes, oh my God, that's an even bigger word. It's the exact same thing. Okay? We're comparing 2 values. That's it. Okay? So if we go through and take a look at some, notice we've got a cheat sheet up there. We've got the English. There are 1,000 meters in 1 kilometer. What you are required to do is convert that English into a mathematical expression. Okay? 1 kilometer, I didn't follow it logically from the written, so let's fix that. We could say 1,000 meters equals 1 kilometer. Because there are qualities, it doesn't matter the order, I now have a mathematical expression. Does that make sense? Okay. With a mathematical expression, I can take things from the left side and put them on the right side. I could take things on the right side and put them on the left side. How would I do that? How can I get this 1,000 meters over onto the other side? I divide both sides by 1,000 meters. What do I get? 1 equals 1 kilometer over 1,000 meters. Those of you saying, well, that's 1/1,000th. No, absolutely not. That is the numerical answer. We don't care about the numerical answer. We care about the units tied to it. The units are what's going to solve your question. So we need to make sure that we drop those units in there. Okay? Did I have to bring the 1,000 over to the right side?
Yes.
No, I could have just as easily taken the 1 kilometer and moved it over to the left. What would the result have been then? 1,000 meters over 1 kilometer equals 1. Okay. The power of this is that this now equals 1. So I can take this expression and I can drop it into any equation I want. The result being, what am I multiplying by? 1. Okay. The power of this is that I now have those units that can potentially cancel other units in my expression. Okay? So what we've generated here is a conversion factor that equals 1. I can multiply any equation I want by 1 because it doesn't change the meaning. Okay? It will allow me to convert units though, and that's a pretty powerful tool. That's why the units need to show up in it. So we're looking at these fractional notations. Pretty much the rest of the semester, that's what we're doing. What is a fractional notation and how do we use it? That's it. Okay? So from here on out, it's boring because that's all we do. Sorry. Okay? We'll reference a numerator and a denominator. Okay? So there were two conversions that we could have come up here or come up with here, or unit factors. They're just a way of saying what are those relationships. Since both of them equal 1 because of the mathematics behind it, I can use either one, depending on the situation I'm in. Okay? So you are responsible for knowing the English and the mathematics, but then you have to use that knowledge to build your conversion factor and to use it at the appropriate time. Kind of, sort of? Okay. We could go through and do it with centimeters as well. Okay. Our mathematics, 1 centimeter equals 1 cm equals 10 to the minus 2 meters. What's the subtle change that I made in this example from the previous one? I'm using my power of 10 instead of what everybody memorized, this 1,000 meters thing. Okay? What I would prefer you to use is a system like this where we're using our powers of 10 because that can help us tie back to that knowledge. Our result is that we get 1 centimeter, 10 to the minus 2 meters. Notice, where's the power of 10 affiliated? Okay, meters true, but I want a different way to describe that. The core unit. Okay, between centimeters and meters, which is the core unit? Meters. It's the one that makes up both units. That's the core unit. So my power of 10 should always get tied to meters. Why does that become weird back with this other one? Oh, in this case it didn't. Actually, I lied. So it worked out okay. The power of 10, 1,000 is 10 to the third. Where am I writing that 10 to the third? With the core unit. Your power of 10 should always get tied to the core unit. This works for 1,000, it works for centimeters. Where this runs afoul is that when we move into centimeters, is that most people don't memorize that 1 centimeter is 10 to the minus 2 meters. What do you memorize? 100 centimeters is 1 meter. That's not wrong, but if we go through and look at that, what's happening? So you said 100 centimeters is 1 meter. 1 meter over 100 centimeters. Your power of 10 shows up where?
Centimeters.
With the centimeters, which is not the core unit. Okay? That memorization or that process there means your power of 10 can show up in different locations depending on which unit you're converting. That requires you know two things. If you just say the core unit always gets the power of 10, guess what? You memorize one thing and you simplify the calculations and you can prevent some of those mistakes. Because well, I'll never make those mistakes. Yes, you will. Okay, we all have. Okay?
Did somebody copyright the symbol for micro?
It's not a copyright, that's an asterisk, and I don't remember what the, oh, I know what the asterisk is about. It's because it's the Greek letter. Whereas if you look at all the other letters, they're not Greek letters, so it looks goofy. It's the Greek letter for mu, so it's kind of an M shape. If you see it written out or typed with people that don't have the proper font, you'll usually see it written as a U, not a mu. It's officially a mu. Okay, so it's a Greek letter. That's what's happening there. Yeah. This one's a little bit weird and throws people for a loop every so often, so if you aren't comfortable with fractions, then you can ignore this. Okay? Let's get at an understanding of what the negative and positive mean mathematically. Okay? 10 to the positive 2 means what?
Multiplying 10 by itself.
10 by itself.
Twice.
Okay? So there we go, 10 to the 2. I have another 10 to the 2. So I'm still multiplying 10 by itself.
No. You're dividing it.
The minus means run that operation in the other location. Where's the 10 to the minus 2 currently written? It's written in the numerator. The minus means run that operation in the opposite location of where it's located. 10 to the minus 2 is currently in the numerator. Where should I run the calculation? In the denominator. Why does it become 1 over 10 to the positive 2 now?
Because anytime you flip it,
Because I flipped it, it's going to change the sign. The minus sign means do it in the other location. The positive sign means do it where it's located. It's currently in the denominator. I don't have to flip it again. Okay. So that minus can help you change your location. That means you can also take kind of shortcuts and try to oscillate your calculation, your powers of 10 in different locations. That usually requires a little bit more advanced on the mathematics skill. If you're not happy with that, don't worry about it. Ignore it and just use your calculator. Okay? But I at least want to address that simplification. This is usually where that 100 centimeters comes in, because 10 to the second is 100. It's running the same calculation, but we're doing it in the opposite location, which means we can change the location of the number. Okay? So that's where that other memorization comes in, just so you know. So the next big part of this is what is conversion. Okay? Everybody looks at it and goes, well, I know how to calculate feet to inches, so I'm not going to do Mike's stupid process. Everybody knows how to calculate feet to inches because you spent the last at least 16 years, maybe, doing conversions of feet to inches. Right? And you've internalized that process. Right? Well, how about seconds to milliseconds? You probably haven't done that all that often, but you might be, oh, powers of 10, I can deal with that, I can just shift decimal points around. Okay? All of the conversions that we talk about within this unit are all things that you have internalized. The problem with that is that if you fight me now and don't learn the process and stop internalizing it, when I switch to moles, you'll be like, well, I don't know how to deal with a mole. Mike must not have taught me anything. That's because the process is what allows you to solve. If you fight the process, you end up screwing yourself over when we switch to units that you can't possibly comprehend. And a mole is one of those. 6.022, already a decimal, times 10 to the 23rd. Power of 10, 23rd, massive number. That is so far beyond human comprehension that we have to say, I can't understand that, I'm going to call it a mole. Okay? As soon as we do that, that simplifies all of our calculations. But we have to be able to acknowledge that and do the conversion, the process behind it. If you don't learn the process now, the mole conversions become an utter nightmare, or more of one. Okay? The point of this section is not to prove that you know how to convert between inches and centimeters, okay? Or feet and inches. I'm pretty sure you can do that. Right? But that's why we're doing it. You can do that, you know what the answer is. Devise a process that allows you to consistently get that answer so that you can start to trust the process. When we move to a place where you can't do the answer in your head, you can now trust the process to get you there. Make sense? Okay, so this is typically referred to as dimensional analysis. And you'll run into tons of people who go, oh, we should never teach dimensional analysis. Everybody is teaching dimensional analysis. They're calling it something else. Okay? So the process that your textbook uses, which is a pretty solid one, comes up with 3 steps. Step number 1, write down what you're trying to get to. Okay? I don't mean the answer. Okay? I don't mean the number. The number is meaningless unless you have the unit. So step 1 is write down the unit that you want for your calculation, or the unit that you're aiming for. Okay? Step 2, write down what you're starting with. Okay? And in particular, the unit of what you're starting with. Step 3, look at what you wrote down. Are the units the same? Okay? If they're the same, that was an incredibly stupid question because you now have the answer. Okay? If they're not the same, you now have to come up with some way to cancel those units using fractions. Okay? Numerator, denominator, where does the unit show up? Do I want it to be there? Do I want it to be somewhere else? Come up with a system to go through and calculate that. Okay? So let's test your knowledge on this. Never mind. I thought, wait, what? I deleted, because we already talked about that. What? Where's my fun question? Well, monkey, we're going back to this. Maybe I was just going to make up the question. Let's make up the question. How many, we'll come back to that thing. How many feet in 36 inches? I know it's a bit of a challenging question. See what you can come up with. If you got your answer, go ahead and hold your hand up. That's a lot of people that have their hands up right away.
The ones that have a calculator.
Okay. Ones that have a calculator, that's a possibility. Okay. Or memorized it. Okay, so let's go ahead and put the hands down. Let's think about it. What'd you do? How'd you get your answer for somebody that got the answer? You said 36 divided by 12? And you got 3. Okay. Well, I argue that the answer should actually be 6.
What?
Because when I take 36 and divide by 6, I get 6.
I did it.
36, 12, and 3 says nothing about feet or inches. 36, 6, and 6 says nothing about feet or inches. What you told me to do for your calculation does absolutely nothing as far as what the question is asking. My answer of 6 is entirely as equally valid as yours by telling me it's 3 because you do not have units associated with that. You need to fix that. Okay, so let's work through, or are you going to give me suggestions on how to fix it?
Yes.
Okay, what are you going to give me to fix it?
36 inches
Yep.
over x equals 1 foot over 12 inches.
Okay.
And you should get 3 feet.
This method is algebra. It's awesome. It allows you to do a single conversion. When we move further into unit 3, you will be doing 3 or 4 conversions. That means you will be writing this 3 or 4 times, making 3 or 4 times the opportunities for mistakes. Okay? Not so hot. Okay? That also does not follow the dimensional analysis system, because what you're saying is what I get is feet over inches. That's what I'm solving for? Feet over inches?
Well, then you cross it.
Should be inches over.
So is it 1 foot over 12
What do I want
inches?
for an answer? I want feet.
Should you be multiplying 1 foot over 12 inches times 36 inches over?
I'm not going to accept that. Go ahead, because I think I saw your answer or hand first. I still don't want to quite accept that. You're saying the same thing he is. You're right. What are you saying? And you're giving me the right answer too. Okay. Let's pull what I will get a lot of people saying, but it sounds like some people are actually following along. Well, 36 inches, okay, right, over 12 feet.
True.
Well, now 36 divided by 12 is 3, right?
12 feet.
It doesn't cancel.
3 what?
3 what? It would be 3
Inches over feet.
inches over feet. Is that true? No. So that doesn't make sense to put feet there. Okay, well, Mike, you're just being a jerk. You actually mean 12 inches. So now it works. 36 inches divided by 12 inches equals 3.
Inches.
Yes, that equals 3. What's the unit?
Inches.
It's not feet.
No, they cancel out.
They cancel out.
So it would just be 3.
What units would I have?
None.
None. This process also doesn't work. Right? So let's go back to the process that you were told to go through and follow. I know I just deleted everything. Unit in your answer. Okay? What was the answer that we were looking for? Feet. Or foots. I'll accept it. Okay? What was our given value?
36.
Inches. Notice, what did I write? Inches. What did I not write? 36. The inches is the unit. That's the part I want you writing first. Yes, 36 is important. I will then write that second. Is 36 inches the same thing as feet?
No.
No. So what does that mean? I need to throw in a conversion factor. This is my step 3. That is that unit factor that your textbook likes to refer to it as. Okay? In that unit factor, what do I want to show up? Okay, well, what shows up in my answer? Feet. Where?
In the numerator.
In the numerator. So what should show up in my conversion factor? Feet in the numerator. So that the units show up in the proper space. Okay? I've now introduced feet into my conversion. This could potentially work. But if I go through, now I have feet correctly in the right spot, but inches would also show up in my answer. I don't want inches, so where should inches show up? In the denominator, so that it can now cancel. Now I have a unit factor, or something that I can work with as a conversion factor. Now that I have those units, I can say what numbers can I put in to tie to those to do that conversion. If you start with the number first, you usually put in the wrong number. Put in the unit first and then be like, am I supposed to know that conversion factor? Well, you tell me. Should you know the conversion factor between inches and feet? Yes. Okay. What is that conversion factor?
1 over 12.
I don't accept 1 over 12. 1 feet over 12 inches. Okay. I'm putting the number next to the unit that was listed. It was 1 feet, 12 inches. Okay. Now what happens when I go through and run the calculation? The inches cancel. Okay. And we had an interesting question pop up. I need a denominator over here. I have one.
An assumed imaginary one.
It has to be 1. If it is not 1, is it 36? No. What is the unit in the denominator? Nothing. Because if it's inches, what happens to my inches? It cancels and I wouldn't have 36 inches anymore. If it was any other unit, it wouldn't be 36 inches. It would be 36 inches per some unit. Okay? So there's an assumed 1 there with no unit associated with it. Now when you track your calculation, you can take everything in the numerator, multiply it out, everything in the denominator, multiply it out. Take the numerator, divide by the denominator, and there's your answer of 3 feet. Okay. Just to be extra irritating, because I'm getting the feeling you guys aren't quite irritated enough, that answer is wrong. Nope. X is a bad idea. It's setting up algebra. That's setting up a whole nother system. This, believe it or not, does the same thing, but it does it in a single step where I can do multiple conversions at the same time. There's no X. Do you guys want a hint or just the answer? Okay, I heard the answer first, so I'm going to give you the answer. You have to tell me then why it is now a better answer. Son of a... Yes, sig figs. It has to be 3.0 feet because 36 is my measurement, which has 2 sig figs. 1 feet has... Nope. Nope. It is not one significant. It is infinite because 1 feet, that's really starting to bother me, 1 feet is 12 inches is a exact value. It's a definition. The sig figs in that conversion factor are infinite, which means our answer needs to get reported to 2 sig figs.
That's sneaky.
Yep, I agree.
So this is kind of test, isn't it?
Okay. If we then think back, because everybody's now like, oh, I'm extra mad now. Okay. If it is a significant figure question, what you will likely see for your answer choices would be 3.0 feet. You would probably also see 3 feet. Let's see if I can come up with another one. I can't do that math, but can somebody do it for me? 36 times 12?
140.
That's totally not true, but I'm going to write it. 104 feet. Okay, I'm just going to write 36 times 12 feet. 432.
Because one will always be ridiculous and wrong.
Yes.
The first one is
40,
just one.
sorry, 432?
Yeah.
Okay. So that's only 4 answers. We're supposed to have 5, so I can give you a ridiculous and wrong one.
That's what 104 was.
Yeah, that's kind of what I was thinking too. I always pick on goats. I don't know why.
Help them like it.
Okay. When we look at those answer choices, we run into a couple things. The very first red flag that should be jumping up, you have 2 answers that are the same value. That should immediately set off alarm bells saying sig figs. Okay, immediately. 104 was a completely random number. Where did 432 come from?
36 times 12.
Why would you ever do 36 times 12?
Bad math.
Because you set up your calculation wrong. You just said, well, I don't know how to do this. I'm just going to start punching numbers into the calculator. 36 times 12. Oh, 432. It must be right because my calculator said that number. Okay? You can't just randomly punch into the calculator. I randomly punch into the calculator as well to give you those answer choices. Okay? And then goats shows up as just a random one. Kind of make sense? So if those were your choices, you should immediately be zeroing in on those top 2 and saying, oh crap, I have to worry about sig figs. Because I'm looking at sig figs, I now need to go back and look at my units given and decide 2 sig figs, the answer has to be 2 sig figs 3.0. Yeah.
Well, then by that logic, you wouldn't even have to do the problem, right? Because if you knew it was a sig fig, then you just look at
By that logic, so let's say that again, by that logic, you don't even have to do the calculation. Abso-freaking-lutely. Anytime we have a sig fig question, you don't have to do the question. You just have to be able to interpret the answers according to your sig figs. You're absolutely right. This is why sig figs get explicitly asked for and very rarely are a secondary input as a multiple choice answer. You're right. Okay. Make sense? That didn't make sense to you? Talk to me after class and we can work through that. I can show you some examples in the practice exams. Okay.
yes.
Okay, so metric conversions. Here's another one. Go through and set this one up. What is the mass in grams of a 325 milligram aspirin tablet? Okay. You should be able to do all of this one. Admittedly, it's kind of mean, but you should be able to do it all. Yes.
Oh,
Okay. What are we starting with?
Milligrams
Milligrams
of aspirin, sorry.
aspirin tablet. The number?
325.
325 milligrams of an aspirin tablet. Are milligrams of an aspirin tablet the same thing as grams of an aspirin tablet? No. So what do we have to do? We have to do a conversion. In that conversion,
Throw grams up on top.
I want grams of the aspirin tablet, which I'm just going to write AT because I'm tired of doing that. Okay. And I will write milligrams of the aspirin tablet on the bottom. Okay. Why?
Because we're going to cancel out.
The milligrams of the aspirin tablet needs to cancel out. The milligrams of aspirin tablet is currently written in the numerator. So in my conversion, it needs to show up in the denominator so that it cancels, right?
So this needs to be a fraction too, right?
Okay. We'll come back to that one. Yep. Okay. So now, have I memorized a conversion factor that I could put in there between milligrams and grams?
yes.
Yes, based off of milli. And milli means
10 to the negative third.
10 to the negative third. Okay. Where does the power of 10 always go?
Grams.
On the
To the unit. Core.
The core unit. Which is the core unit? Grams or milligrams? Grams. So I get power of 10 to the minus 3 in front of the grams. Oh. What shows up on the bottom? 1. Pause. Don't freak out too much because your calculation may have been correct. Okay? I can now enter it into the calculator and I'd get my answer. Okay, the calculator should probably spit out 0.325, and that would be correct with sig figs and all that fun stuff. We have our grams, right? Everybody okay with that? Okay. I went through, so well, let's go ahead and address that. Okay, so we've got a
That
suggestion.
answer, but I didn't do it. Apparently
325, no, that's actually not true. You did do it right. 325 milligrams. I'm not going to write the aspirin tablet out again because I don't want to do that. Okay. Now we got a suggestion that 1,000 milligrams is 1 gram. Is that true? That is absolutely valid. The 1,000 goes in front of which unit? Milligram.
I know one.
The 1 goes on top.
I know one.
What do you get for an answer?
Same thing.
The exact same thing.
I know one.
There is no difference. Okay? We should all know why.
Because the negative flips it.
Okay? Based off of what we talked about with that mathematical operation with 10 to the negative 3. The negative means run the calculation in the opposite location of where it is. Where is the 10 to the minus 3 currently located?
On the top. So
On the top. So I need to do 10 to the third on the bottom,
Which is about.
which is 1,000. Okay? The issue I have with this method is that you have to know that 1,000 milligrams is 1 gram. Okay? Well, that's not that big of a deal. Okay? Your power of 10 is affecting milligrams. Okay. How many kilograms and grams? What's your conversion factor there?
1,000 grams.
1,000 grams is 1 kilogram. Where did your power of 10 go? In front of the core unit. Where's your power of 10 going here? Not the core unit. Okay. Because of the memorization on which direction it's going, someone went through and said it's easier for me to memorize the multiplied out number than it is the power of 10, so I'm going to memorize the multiplied out number. Unfortunately, that requires that you have to memorize the relationship between milli and not milli. You have to memorize the relationship between kilo and not kilo. You have to memorize the relationship between centi and not centi. You have to memorize all of those relationships to ensure that when you put in your power of 10, that you're placing it in the correct location. Because it will change. Okay. If we follow how I said to memorize the Greek prefixes. Okay? The power of 10 always, without exception, goes where? In front of the core unit. There is no secondary memorization on knowing which one's bigger or smaller. Okay? And for me, just thinking back to what I had to deal with as a student and what listening to tutors go through and talk about conversions. They go, well, okay, milligrams versus grams. You wrote in, so you wrote in this. And they go, okay, well, which one's bigger? Is that the same? No. Right? When they're saying which one's bigger, grams or milligrams. Well, if I knew that, I wouldn't be making this mistake. Okay? If you're doing this and placing or misplacing your numerical values, it's because you're confusing what you've memorized and then losing track of how you've memorized it. Because you're doing it in your head. Your head is a nasty, scary, freaky place to be. You will screw it up every time you do it in your head. Okay? Take it a step further. If you do it in your head on a show your work question, I can't give you any credit, period. Even if you get the answer right. So don't do it in your head. Write it down. Pick a method that is consistent always. If you can consistently memorize the 1,000 milligrams in gram, that's because now I'm going to say it backwards. Got to fix that. Sorry. That 1,000 milligrams is 1 gram, and that you can memorize that 1,000 grams is 1 kilogram, and never get it confused, by all means, keep doing it. Right? The issue is I've seen too many times people misplacing the numbers because they have an inconsistent method. It will work once, may even work twice, but the third time it usually fails, and that's usually during the exam, and you can't figure out why you're making the mistake. Pick a consistent method and stick with it. The method that we walked through, your power of 10, always goes with the core unit, will always work. Assuming you also memorize what those Greek prefixes meant. Okay? It seems like such a silly thing to talk about, but it makes a really big deal. We okay with that? Okay. And when you make that mistake, I will point it out and I will try to be kind about it and be like, this is why I told you to not do it that way. That's okay. We'll try and get you to fix it one way or another. As long as you're consistently correct, I'm okay with it. Okay? The last thing I want to address, because I saw a couple people doing it, well, it was 10 to the minus 3, so that just means I shift the decimal point. I'm really sorry, but you should not be doing that. Right? The reason being, well, if I just shift the decimal point, I just have to shift it. You know, I just shift it to the left. Okay, what if you were supposed to shift it to the right? You now have to memorize that extra step of which way you shift it. Okay? Depending on what number you're looking at, you may be shifting it left, you may be shifting it right. You're at a 50-50 shot at best. That 50-50 is going to work for you here. It won't work for you on the exam. Show the work. Okay? And again, I press the showing the work so much because I have screwed it up on more than one occasion by not showing the work. Okay? So I will write it out. Okay? So please, write that work out. Do you want to try and do this one now?
No.
I heard a no outright. Okay, let's go through with a yes. I'll solve it with you guys. What do we want for an answer?
Micrograms.
Micrograms. So what is our mass in micrograms? So we're specifying the unit. That's that goofy mu. Okay, again, it's the aspirin tablet. Okay, so I will go through and write AT this time. What am I starting with?
Milligrams.
Oh, you caught me. Milligrams of the aspirin tablet, and I happen to have 325 milligrams of that. Thank you for catching that. Okay. For those of you that didn't see the mistake, what I wrote down was started to write the number. Focus on the unit. Okay? So, I will now set up a conversion, because milligrams is not the same thing as microgram. The ideal situation, okay, and this is how we should approach everything. Don't make it more difficult if you don't have to. The ideal situation, is that milligrams shows up on the bottom so that it cancels. What would show up on top? Micrograms of the aspirin tablet. For those of you good with doing your powers of 10, shh. For the rest of us, which includes me, do we know a conversion between milligrams and micrograms? No. Shh. I know that milligrams I can convert into grams, and I know I can convert micrograms into grams. So this conversion for me is not a valid conversion. I don't know the numbers that I can put in there. Yes, I could potentially look it up, which we would kind of have to any case because it's a micro. Okay? But for me, I don't know that conversion. So what I'm going to do is say, well, if I can't convert it directly, I'm going to convert it into something that I know I can convert into. I can convert milligrams into grams. Okay?
So you have to change the far right.
I could then go through and change the far right. This is the benefit of setting it up in dimensional analysis and not solving for x. I don't have to change the far right because the far right is what I want.
Just do it.
After my first calculation, I won't have what I want.
So you put grams at the bottom.
So I will put grams of my aspirin tablet on the bottom. And what do I want? Micrograms at the top. Right?
Is micrograms with a capital M?
It's a mu. It's a Greek mu. It's a Greek letter that looks an awful lot like my M because I'm handwriting it. But that's the best I got.
Y attached to a U.
That's why I usually try and throw a little tail on it so that it stands out a little bit
Could
different.
you spell that?
If we just use the letter U on the exam to avoid confusion, would you mark that wrong?
No, I wouldn't. I'd accept you.
What if we write out the word U?
You could write out mu. I'm fine with that. What's that?
I said I would accept you too. Get it?
That's not maybe.
The grams aspirin tablets cancel. Our milligrams cancel. And I'd be left with micrograms. It's exactly what I want. So my units are set up. Now I need the numbers associated with said units. Okay. What is the conversion between grams and milligrams? Well, what did milli mean?
Negative third to the 10.
10 to the negative 3. You'll notice I'm not saying thousandth because that is too hard for me to say and hear appropriately. So milli means 10 to the negative 3. The 10 to the negative 3 shows up where? I do not accept top. I do accept the core unit. 10 to the negative 3. 1 shows up in front of our milli. We move to the next one, grams to micrograms. That's one I would have to look up. Micro meant 10 to the negative 6 shows up where? In front of the core unit, which is grams. Okay. Now I can punch it in the calculator and run this out. Okay. Just because we heard someone go through and do this math either in their head. Did you do it in your head or did you look it up? That's fair. 10 to the minus 3. Come on, pen. Minus 10 to the minus 6. This is the same as saying 10 to the minus 3 times 10 to the 6th. Because my powers are the same, I can then add those units. 10 to the negative 3 plus 6, which equals?
Positive 3.
And you said it was?
1,000.
1,000. What is 10 to the third? 1,000. They come out the same.
Then how much is
Okay.
125?
So all we'd have to do is then multiply the 325 by 1,000 and we'd have our final answer. Apologize for going long. Thank you this time for not all getting up.